Okay, my friends. So I actually already recorded all of this and ran into the problem where it actually wasn't recording. So super fun. I'm just gonna start again. And where the last video left off was on slide 39, question 13. All right. So let's just pick it up right there. So question 13 says a piece of lead absorbs 100 joules of energy and its temperature increases 15 degrees. What is the mass of this piece of lead? And it gives us the specific heat of 0.13 joules per gram degrees C. So this is like so many, a Q equals ms delta T problem. Okay. And we have the Q. And it says that the lead absorbs 100 joules of energy. So if it's absorbing the energy, Q should be positive. Let's see. And then it says its temperature increases by 15 degrees. So delta T is 15 degrees C. And we're given the S as 0.130 joules per gram degrees C, right? So we want to know what is the mass. All right, so let's look at our equation and rearrange it to solve for the mass. Mass delta T. So in order to get the mass by itself, I'm going to divide S delta T to both sides. So what I get is mass equals Q over S delta T. So with that, I can just plug in my numbers. Equals 100.0 joules. And remember to put this part on the bottom in parentheses so that your order of operations don't foil you. Okay, joules per gram degrees C times 15 degrees C. And noticing that delta T is only 2 digits, so our final answer should come out to be 51 grams. All right, so at slide 40, we start talking about coffee cup and bomb calorimeters, okay? And question 14 is where we get into the calorimeter stuff. Okay, so a chemical reaction takes place in an aqueous solution inside a coffee cup calorimeter. All right, so 14. Coffee cup calorimeter problems are always going to be ms delta T problems. Okay. And it says that a reaction takes place in an aqueous solution. That means that it is a solution in water. Okay. So that tells us right away that our S is the same as that of water. 4.184 joules per gram degrees C. Okay. And our mass is told that the mass of the solution is 110 grams. And it says that the temperature increases by 5 degrees Celsius. So our delta T is 5.0 degrees Celsius. Okay, so it wants to know how much heat has the solution absorbed. All right, so we're just going to set this up as a Q equals ms delta T problem. 4.184 joules per gram degrees C times 5 degrees C times 10 to the 3 joules. So I do apologize, I'm left-handed, and so quite often my hand will hit the screen in funny places and cause weird things to happen. The world is not a left-handed world. But anyways, I'm used to it. I just like to gripe about it once in a while. Okay, moving on. So question 15 is a bit more complex, okay? So in question 15, we have a hot piece of metal placed in a coffee cup calorimeter, okay? And then after some time, the water warms up to a particular temperature. Okay, let's think about what is really happening there. So we have a hot piece of metal being dropped into cool water. So the metal's going to cool down, the water's going to warm up a little bit, and eventually those two things will end up at the same temperature. Okay? So it says that after some time the water warms up to 20.28 degrees Celsius. That means that the metal is also at 20.28 degrees Celsius at the end. Okay? So T final for the water is the same as T final for the metal. All right, so it says that it's a coffee cup calorimeter problem, so it's still an MS delta T situation. But we have Q for the metal and Q for the water. So we'll deal with that here in a second. So let's make our list like we have been. So mass of the metal we are given is 10 grams, right? We're given the initial temperature of the metal, because it says the metal is heated up to 100 degrees and then placed in the coffee cup calorimeter. So our initial temperature for the metal is 100 degrees. And then the metal and the water eventually both end up at the same temperature. So that's the same for both, the 20.28 degrees C. Okay. Now, we also know about the water. So mass of the water is 75 grams in the calorimeter. We know the initial temperature of the water is 18 degrees C. And we know T final for the water is the same for the water and the metal, like this, right? So, what's delta T, right? Let's remember delta T equals T final minus T initial. Right? So over here for the metal, delta T equals 20.28 minus 100. Right? So we end up with a negative value for that temperature. 20.28 minus 100 gives us a negative 79.72 degrees Celsius. Tracking right there because there's no decimal place on that 100. Okay, and then over here for the water, T final is 20.28. T initial is 18. Comes out to 2.28. And we're tracking at that decimal place. Okay? So just as a warning that delta T thing is, I'm going to remind you that that's a subtraction problem, and the sig fig rules for subtraction are concerned with decimal places, not sig figs. Okay? So, the last thing that we know, even though it's not specifically written in the problem, is the specific heat of water. Okay? So, now, for the water, I have the mass, the specific heat, and the delta T. So I can find Q of the water. Now, we already talked about what's happening is that the metal's cooling down and the water's heating up. So the amount of heat that comes out of the metal is exactly the same as the amount of heat that goes into the water. So here is a very important relationship. So the heat that comes out of the metal, it's negative because the heat is coming out, equals the heat going in to the water. Okay? That's a very important relationship. So if I can find the Q of the water, then that tells me the Q of the metal. And I can use that to find out whatever else I need. Okay, so let's go ahead and find Q of the water. And it was 75 grams times the specific heat times the delta T. Okay, so that comes out to be 75 times 4.184 times 2.28. Remember, we're tracking right there for the sig figs. So Q the water equals 715.464 joules. Tracking at the second sig fig. Okay. So if this was all that I was being asked, I would round that to that second digit, and I would say 7.2 times 10 to the 2 joules. Okay. But I'm not done yet. Okay. By this relationship, this one right here, that means if I know Q of the water, then Q of the metal is just negative of that. That's a 6. Okay? Now eventually, the question wants to know what's the identity of the metal. And in order to find out that identity, I need to find the specific heat. Okay, so stop. And we're going to solve for the S. So S equals Q over M delta T. Okay. For the metal. All right, so S for the metal is negative 715.464 joules divided by the mass, which was 10 grams, and the delta T is that guy, negative 79.72. Okay, tracking at that second sig fig. Okay, this works out beautifully because our negative Q and our negative temperature, the negatives will cancel out and give us our positive value because the specific heats should be positive numbers. All right. So let's see what that number is. 10 times 79.72. All right, and we're looking for a 2 sig fig value, so it should come out to be 0.90 joules per gram degree C. Okay? And then we look on our table and we find that aluminum is 0.897 joules per gram degree C. Nothing else is even close, right? And that 0.897 would round to 0.90 if we were looking for 2 sig figs. All right? Question 16 is exactly like question 15, and remarkably almost exactly identical to question number 7 on your worksheet. Okay, so it's the same situation, right? Chemist conducts a calorimetry experiment on an unknown metal. The mass of the metal sample is 52.4 grams. The chemist heats the metal to 100 degrees, then places it in a coffee cup calorimeter containing 95.4 grams of water. And the temperature of the water rises from 21.9 to 23.2 degrees Celsius. So question A is asking for what is the heat change of the water. Okay, and that's exactly like what we did in the previous problem. All right, it's a coffee cup calorimeter problem. So Q equals MS delta T. Okay, So let's make our lists so we know the mass of the metal is the 52.4 grams. We know the T initial of the metal is 100 degrees Celsius. We also know the T final because remember the water and the metal end up at the same temperatures. So T final for the metal is the same as the T final for the water. Okay, so delta T, final minus initial, is delta T of the metal is negative 76.8. Okay. And then we also know the mass of the water, 95.4 grams. T initial for the water is 21.9. T final for the water is 23.2. So delta T equals 1.3 degrees. Okay? And again, even though it's not specifically written in the problem, we also know the specific heat of the water. Right? So, first question says, what is the heat change of the water? So Q equals ms delta T for the water. So let's see, 95.4 times 4.184 times 1.3. Q of the water equals 518.89968. Tracking at the second sig fig. So I'm going to say 5.2 times 10 to the 2 joules. Okay? Excuse me. All right, so just like in the previous problem, the heat coming out of the metal is the same as the heat going into the water. Okay? So we just figured out that the water absorbed that much energy. So that means that Q of the metal, and this is question B, by the way, Q of the metal is just negative of that. Negative 5.2 times 10 to the 2 joules. Okay? And then question C wants us to find what is the specific heat of the metal. Okay? So, Q equals ms delta T. We want S by itself. Oops, we don't want Q, we want S. Q over M delta T. Okay, looks like it says mat. Q mat. All right, so specific heat of the metal. And I'm going to use that whole number. Okay, so I don't end up with any rounding issues. Negative 518.89968. Second sig fig. That still counts. Okay, and then our mass of the metal was 52.4 grams. And our delta T was, let's come back up here, 76.8 right there. Negative 76.8 degrees C. Which comes out to be S equals 0.13 joules per gram degree C. Okay, so those two problems, 15 and 16, are exactly the same type of problem, and they're just like question 7 on your worksheet. Okay. I'm just going to take a real quick check to make sure that I'm still recording, and I am, okay, because I don't want to re-record this a third time. All right, so when we hit to slide 49, it's starting to talk about something called a fuel value, okay? And a fuel value is simply the amount of energy in a given amount of mass of a thing. Okay, so looking at question 17, we have a table of common fuel values, right? Like 55.5 kilojoules per gram of methane. So if I have 1 gram of methane, then I can get 55.5 kilojoules out of it, okay? Now those fuel values are conversion factors, okay? We love that word, don't we? Conversion factor, okay? But that's all they are. And so we can use them just like any other conversion factor that we've done. Any of our metric things, any of our mole ratios, they're all just conversion factors, right? Hopefully everybody's remembering to practice their metric conversions and their nomenclature. Hint, hint. So let's see. Checking out question 17. How much energy in kilojoules would be released by the combustion of 0.50 kilograms of butane gas? All right, and we look in the table and we find that butane has a fuel value of 49.5 kilojoules per gram in 1 gram. Okay, now I can write that as a conversion factor. So if I need to, I can flip it or do whatever I want to it. Okay. Well, not whatever I want to it, but I can flip it upside down or however I need it to be, okay? So my problem is giving us our given information in kilograms, okay? So I need to put that in grams in order to make this work, all right? So remember our metric conversions. So there's 10 to the 3 grams in 1 kilogram, okay? And then I'm going to use my fuel value up here. The fuel value up here, I forget that you can't see my hand gestures. And I'm going to write it so that the grams go on the bottom because I want the grams to cancel out. So 49.5 kilojoules in 1 gram. Okay. So if I'm careful with my labeling, my kilojoules will cancel, my grams will cancel, leaving me with an answer in kilojoules, which is what I want. So we end up with 2.5 times 10 to the 4 joules. No, excuse me, kilojoules. Okay. Moving on, looking at question 18. Well, quit it with the zooming. Okay, question 18. Methane has a formula of CH4. How much heat is released by the combustion of 1 mole of methane? Okay, now all of our fuel values are in kilojoules per gram. So I need to put my moles in grams. All right, so if we have a formula, CH4, that means I've got 1 carbon and 4 hydrogens. So carbon, 12.01 grams per mole. Hydrogen, 4 times that, 1.01 grams per mole times 4. So it comes out to be 16.04 grams per mole, right? So I've got 1 mole of CH4. I'm going to convert that to grams, so I'm going to put moles on the bottom and grams on the top. Okay. And then my fuel value for methane is in the table. So in that one is 55.5 grams, not grams, kilojoules in 1 gram of methane. Right? So our moles of methane go away and our grams of methane go away, leaving us with kilojoules. That equals 8.91 times 10 to the 2 kilojoules. Okay? So by now, you guys are really, really good at conversion factors. Okay? You know how to go from grams to moles, moles to grams, calculating formula mass. We're asking you to combine a lot of things in order to accomplish these problems, okay? So there's no one-size-fits-all problem. You have a lot of skills with you now, and we're asking you to start using them in conjunction with each other. All right, so we're at our next to last slide, slide 54, okay? And what 54 is talking about is a thing called enthalpy, okay? And basically, enthalpy is the same thing as heat, all right? But it's sort of a different thermodynamic value, but essentially it's the same thing as heat. Okay, and slide 54 talks about the difference between melting and freezing. Okay, and the enthalpy for melting is exactly the same as the enthalpy for freezing, but in the opposite direction. Okay, so when we melt something, we're putting energy in, and when we're freezing something, we're taking energy out. Okay, but it's exactly the same amount of energy, just opposite sign. Okay. Now, question 19 is talking about reaction enthalpy, okay? And reaction enthalpy is simply delta H, Rxn. Rxn stands for reaction, and delta H is the enthalpy. So delta H, Rxn is the reaction enthalpy, right? And then it says, so when it's talking about a chemical reaction and energy related to that chemical reaction, that's delta H Rxn, okay? The delta H of reaction enthalpy, right? So question 19 says that magnesium carbonate decomposes to magnesium oxide and carbon dioxide gas with the absorption of 100.7 kilojoules per mole of the magnesium carbonate, okay? So that's talking about the chemical reaction absorbing 100.7 kilojoules per mole. All right? So that's our reaction enthalpy. Now the question asks us to write the balanced chemical equation and the reaction enthalpy. So first we're going to write the equation. So everybody remember the formula for magnesium carbonate, right? MgCO3, because magnesium's a 2+ and carbonate's a 2-. So I just need one of each. And it says that it decomposes into magnesium oxide, right? Also a 2+, 2- for magnesium oxide, and carbon dioxide gas, right? And lucky for us, it's already balanced because I've got 1 magnesium on both sides, 1 carbon on both sides, and 3 oxygens on both sides, okay? And then right next to it, I just say delta H Rxn equals, and it says that the reaction absorbs 100.7 kilojoules, okay, per mole. So if it's absorbing, the energy is going in, so it's going to be positive, 100.7 kilojoules, okay? So that is really all that question's asking. The hardest part about it is figuring out what the chemical equation is. Right? And that does it for our Chapter 8 slides. That is it. That's all. I hope that this was beneficial and useful to you all. I'm going to keep posting these things. The first one is already on YouTube for you to see. I'm going to put this one up there as well. So have fun and good luck. And if you have questions, please shoot me a message.